Okay, good morning, Denmark, Christine, and Noriel. And this week we'll start talking about Module 9. This is, I think, the third to the last module for the course. So we are really winding down the course by looking more with looking at more numerical integration formulas. So last time we talked about the use of Newton-Cotes quadrature formulas, and we've seen that that is a simple fix to numerical integration problems, which addresses the three main concerns that we had with the symbolic integration process or whenever dealing with discrete data na gusto nating kunan ng integral, right? So the basic idea about Newton-Cotes quadrature formulas is that we get the interpolating polynomial passing through the data points, and that gives us quite a leeway kasi sa Newton-Cotes quadrature formulas, hindi natin kailangan na or walang requirements sa exabytes kung ano yung present na exabytes dun sa data or whatever exabytes you feel you want to use ay pwede mong gamitin. Hindi kailangan equally spaced yung data, hindi kailangan na piliin with some criteria, yung mga exabytes. So sila lamang yung talagang available or you can choose them conveniently, say, to be equally spaced points over an interval. So it's up to you, right? Napakalaki ng leeway. And the idea is, kasi kahit sa, the idea kung bakit pwede yung gawin, ay dahil nag-fit lang naman tayo ng isang polynomial. In particular, we are finding the interpolating polynomial para dun sa function na yon using the given data points. So tapos yung yung interpolating polynomial na yon, siya yung i-integrate natin instead of the integrand, which might have some issues like the non-existence of a closed form for its antiderivative, or if the antiderivative is much more complicated than the given function itself, and yeah, and also if discrete yung set ng data. Okay. Now, that is an example of a quadrature rule na sinabi nga natin last time. Yun yung focus natin for the two two modules in the course. So, but perhaps I should mention that later. Let's just have some important housekeeping notes here. This would be the module 9 will be the reference for this week's discussion. The synchronous lab session for this module is on the 29th. That's on this coming Monday. And the second part of Lab Exer 5 will be due on the 29th, also right before midnight. And that is included at the end of this module. So ano yung kailangan natin gawin for this particular module? Number one, we will look at the derivation of some Gaussian quadrature rules. So makita nyo dito, iba tong class ng pang-approximate sa integral aside from the Newton-Cotes formulas, pero quadrature rules pa rin sila. And second, we want to use this quadrature rules to solve scientific problems. And then I also have a bunch of references here. Actually, I added a couple. This one is the book by by Abramovich and Stigan. This is a very useful book, especially if you're dealing with the modeling of physical phenomena. I came across with this when I'm working for my PhD dissertation kasi yung mga functions involved, say, in the propagation of acoustic and electromagnetic waves ay maganda yung pagkakasummarize ni Abramovich and Stigan. And I just actually when I came across with the formulas for the what do you call this, for the weights and the abscissas for the Gaussian quadrature dito sa book na to. So before, when I was teaching 174, before I didn't give the actual formula for the or the generic formula for the weights associated with Gaussian quadratures. Pero when I came across this reference, meron siyang magandang description ng mga weights at saka abscissas. Makikita niyo mamaya kung ano yung kailangan kung paano kino-compute yung mga weights and abscissas. And then next time on Friday, we're gonna see paano siya na generalize ni Stigan at saka ni Abramovich. Okay. And then there's also a nice Wikipedia page about Gaussian quadrature rules, so you can visit it out. Okay. So tama naman yung entry dun sa Wikipedia, so it's safe to use that as our reference. So, but basically, as you have seen in the objectives, Gaussian quadrature rules yung gusto nating tingnan, and they are still quadrature rules. Remember, a quadrature rule that approximates the integral of a function f over the interval a, b is sort of like a formula, or is sort of just taking the linear combination of function values. So we take function values over some exabytes times associated weights with each of the function values. We sum it up from 0 until n. Okay? We are using n plus 1 points. So ito yung itsura ng isang generic quadrature rule. When we talk about the Newton-Cotes formula or the Newton-Cotes quadrature rules, ang itsura naman nung pang-approximate natin ay summation ng f of x by times the integral of the Lagrange interpolating polynomial over AB, okay? Aside going from 0 to n. So kung ano man yung given function values times the integral of the associated Lagrange interpolating polynomial, and this guy serves as the weights wi for each of the function values. Now, in this module, we will be looking at a different way of choosing the weights. And actually, the choice of the weights will be accompanied by properly choosing the exabytes. So yung Gaussian quadrature rules, hindi tayo free na gumamit ng kahit anong exabytes na gusto natin. So, ang gagawin natin, may specific criteria tayo na ibibigay sa mga exabytes at saka sa mga associated weights nila. So, giving us probably some nice measure of error. So sa Newton-Cotes, kung anong exabytes yung available, yun yung gagamitin natin. There's no big problem about that. Pero yung Gaussian quadrature rules, we are choosing the exabytes according to some measure of optimality. So pinipili natin sila to satisfy some nice property along with associated weights W sub I. So we don't get a free rein on the choice of the exabytes pagdating sa Gaussian quadratures. So fixing yung exabytes ng Gaussian quadratures, so we can only use this whenever we have access to the actual function little f. Kung meron tayong way para ma-plug in yung mga exabytes na kailangan sa Gaussian quadrature papunta dun sa integrand. So, yun yung isa sa mga main differences niya with Newton-Cotes. Sa Newton-Cotes, kahit anong exabytes pwede nyo gamitin kung ano yung available mula dun sa problem or mula dun sa data. Sa Gaussian, pinipili natin yung exabytes optimally. So therefore, you cannot simply just use it for an arbitrary set of discrete data kasi nga fixed yung mga exabytes na kailangan yung gamitin sa Gaussian quadratures. So the next big question is, ano yung measure o ano yung criteria para sa pagpili ng mga exabytes? Now, it involves the concept of degree of precision. So let me just make a couple of corrections here. I think, okay, and this should be P. Okay, so there you go. Definition 9.1, it defines the degree of precision. It says the degree of precision of a quadrature rule I sub n is the least positive integer m such that the integral of p of x dx from a to b is not equal to I sub n of p for some polynomial p of degree m plus 1. So sinasabi sa definition, yung degree of precision, say m, siya yung pinakamaliit na positive integer na merong isang polynomial of degree m plus 1 na hindi eksaktong na-approximate nung quadrature rule yung integral ng polynomial na yon. So, ibig sabihin, ito yung degree nung kauna-unahang polynomial. Paano ko ba i-phrase? Siya yung unang degree kung saan makakakita ka ng isang polynomial na hindi eksakto yung approximate na nakukuha mo mula dun sa quadrature rule para dun sa integral ng polynomial na yon. Okay? So probably it's much easier to think of it this way. Mas gusto ko yung alternative definition na makikita natin dito. It is the greatest positive integer for which the formula gives exact value for the definite integral of all polynomial of degree at most n. Okay. So ibig sabihin siya yung pinakamalaking degree kung saan siya yung pinakamalaking degree ng mga polynomial na kaya niyang i-approximate yung integral exactly. Okay? So, ibig sabihin, pag in-apply ko, halimbawa, kung meron akong degree of precision 3, okay? Yung quadrature rule, ibibigay niya sa akin eksakto yung integral ng kahit anong polynomial with degree 3 or less, pero merong isang polynomial of degree 4 kung saan hindi na eksakto yung binibigay niyang approximate para sa integral. Okay? So, ibig sabihin, kahit anong polynomial of degree 0, degree 1, degree 2, or degree 3 na i-feed ko dun sa quadrature formula, ang ibibigay sa aking sagot ng quadrature formula ay yung eksaktong value ng definite integral ng mga polynomials na yon. But I can find at least one polynomial of degree 4 na hindi na eksakto yung approximate galing sa quadrature rule compared to the actual integral of that polynomial of degree 4. Okay? So yun tinatawag natin na degree of precision. Ibig sabihin siya yung degree na kayang i-approximate ni quadrature rule yung integral sa lahat ng polynomial of that degree and less. Okay? So let's take a quick look at one familiar quadrature rule, yung trapezoidal rule. And the question in this first example is how precise is the trapezoidal rule? So kailangan nating hanapin ano yung mga polynomials or ano yung degree ng mga ano yung degree for which the trapezoidal rule can exactly give us the value of the definite integral of polynomials of those degrees. Okay? So, usually, if i-feed mo dapat kay trapezoidal rule lahat ng constant polynomials, titingnan natin kung eksakto ba yung integral na binigay niya. If i-feed ko lahat ng linear polynomial, i-check ko eksakto ba yung value yung value na binigay ng quadrature formula compared to the actual integral. Tapos, lahat ba ng quadratic, cubic, quartic, quintic, and so on. Kung saan ako unang may makitang polynomial na hindi na eksakto o hindi na zero yung error dun sa approximation, then that's gonna be the degree of precision, or the degree of precision would be one less than that. Okay? So, well, we can take advantage of the theoretical results we had last time, and we have seen that the error involved in the trapezoidal rule involves this factor. I guess it has a negative sign before, but actually it doesn't matter too much for our purpose here. So, ito yung factor na makikita natin dun sa error. Okay? Now, we will analyze this function f kasi titingnan natin ano yung mga inputs dun sa quadrature formula na polynomials na eksakto yung nabibigay niyang approximate. Alright? So what are the little f's? Where little f's are polynomials, ano yung mga degree nila na nagzizero yung error? So we're looking for what are the f's, or what are the polynomials f for which the trapezoidal rule gives an exact value para sa kanilang integral, for their integral. Okay. Now, if we look at if f is a constant function, right? So kung si f ay constant function, yung f double prime would be 0. The derivative of a constant is just 0, right? Evaluated at some number c, 0 pa rin siya, so the error vanishes. So ibig sabihin, kayang i-integrate ibigay ni trapezoidal rule ang integral ng kahit anong constant polynomial, eksakto, with 0 error. Now, if little f is a linear polynomial, all right, f double prime is still 0, all right? Then if you plug inside, that will just still be 0, and hence the error term still vanishes. So okay pa, lahat ng linear polynomials na approximate ni trapezoidal rule exactly yung integral nila. But when we go to quadratic polynomials, yung derivative ng quadratic polynomials, or yung second derivative ng quadratic polynomials ay constant, all right? And that constant is not necessarily equal to 0. So we can find at least one quadratic polynomial na yung f double prime at c over 2 ay hindi nagsi-zero. Okay? So making the entire error term not equal to 0. So we are guaranteed to find at least one quadratic polynomial for which the trapezoidal rule cannot give us the exact value of its integral. Pero lahat ng linear functions at lahat ng constant functions na approximate niya yung integral exactly. So that being said, we can say that the trapezoidal rule is of degree of precision 1. Okay? Unang beses na hindi magbibigay ng eksaktong integral si trapezoidal rule ay sa quadratic polynomial kasi ang degree of precision niya ay 1. Okay? Now, you probably have guessed it right. We will be choosing the exabytes and associated weights to them sa Gaussian quadrature rules by maximizing the degree of precision. Okay? So yung mga quadrature rules that aims to find the maximum degree of precision for a fixed number of points is called the Gaussian quadrature rule. Okay? I think I highlighted that here. But it seems that this is a daunting task. Kasi para mahanap yung degree of precision, kailangan nating i-guarantee na kung siya ay degree of precision m, dapat nating i-prove na eksakto yung integral na makukuha ko para sa lahat ng polynomials of degree m or less. Tapos pakita ko na magkakamali na siya sa isang polynomial of degree m plus 1. So kailangan kong i-consider lahat ng mga polynomials belonging to the same class. However, to uh, to uh, to reduce the burden of doing that, we can take advantage of the linearity of the definite integral, plus the fact that the polynomials 1, x, until x to the power n forms the basis for all polynomials of degree n or less. Tama? I think we have seen this in one of the bullets in Legendre polynomials na nagpo-form ng basis para sa vector space of all polynomials of degree n or less yung monic polynomials 1, x, x squared, x cubed hanggang x to the power n. And if you have taken linear algebra, either math 120 or math 105, makikita nyo ron na pag meron kang isang linear operator, kailangan mo na lang pag-aralan yung action ng linear operator na yon sa basis elements ng isang vector space. And with an understanding of that, you can deduce the properties of the linear operator with regards to the entire vector space. So ito yung isa sa mga dahilan kung bakit tayo nag-aaral ng basis para sa mga vector spaces sa 120 and 101. Kasi kahit anong linear map na nag-a-act sa vector space, supposedly pag-aaralan mo dapat paano nag-a-act yung linear operator na yon sa buong vector space. But your work will be considerably reduced by just looking at how the linear operator acts on the basis elements. Kasi pag alam mo na kung paano siya nag-a-act or paano siya nakikipag-interact dun sa mga basis elements, alam mo na rin sort of kung ano yung nangyayari sa buong vector space. And we can take advantage of that pagdating dun sa pag-check ng degree of precision. Okay? Now, don't worry if you haven't taken 120 or 101, 105 yet. Ganito lang yung idea. Okay? So, di ba, para malaman kung ang degree of precision niya ay n, kailangan nating unang ipakita na na-integrate niya ng eksakto yung mga polynomials of degree n or less. So, we can take a generic polynomial little p here. So, a sub 0 plus a1x until a sub n x to the n. Okay? Tapos, ang mga a sub i's lang natin dito ay constants. And then we want to see what is the integral of this polynomial p. Okay? So if we put the polynomial p inside the definite integral, we're going to get this one. Okay? And then again, distributive or additive naman, hindi pala additive, we can distribute the integral over the sum. So pwedeng term by term yung integration kung gawin. Okay? And that's what happened in the next line. And then yung scalar factors dun sa integrand, pwede siyang lumabas dun sa integral. All right? So basically, the integral of p can be written this way. So paano natin mag-guarantee na eksakto yung integral kay p? Hindi ko kailangan i-consider or i-check yung integral ng lahat ng posibleng polynomials. It turns out that looking at this, okay, I can just check if my quadrature rule can give me exactly the integral of 1 over the interval ab, the integral of x over the interval ab, the integral of x squared until the integral of x to the power n. So, ibig sabihin, kung yung integration formula natin, yung quadrature rule nating made-develop, ay eksakto yung binibigay na value para dito sa mga encircled integrals in this form, eksakto yung makukuha kong integral para kay p, kahit ano pa yung mga constant multipliers involved with them. So the task of checking the integral of infinitely many possible polynomials of a particular degree, kailangan na lang nating tingnan kung eksakto ba yung binibigay na value ng quadrature rule para sa integral ni 1 ni x hanggang x to the power n. And this will constitute the major building block in our algorithm to develop the Gaussian quadrature formulas. Because again, the Gaussian quadrature formulas aim to find the abscissas and weights to achieve the highest degree of precision. Okay? So, pero ganun pa rin yung goal kasi quadrature rule pa rin siya. Ito yung gusto nating ma-develop na formula. Okay? And this should be true for all polynomials of degree less than or equal to some constant number, all right? And that constant number should be the maximum performance possible for a fixed number of points. Tapos pipiliin natin yung abscissas at saka yung mga weights to get that, okay? So in the development of Gaussian quadrature rules, first we must fix the number of points. So say we have decided to use n points in our quadrature rule. Kung n points yung gagamitan ko, all right? Ibig sabihin meron akong 2n unknowns. Ano yung mga 2n unknowns na yon? So for each point, unknown yung exaby, which is basically the point involved. And second, unknown din yung weight para sa kanya. So for each point you decided to use, may dalawang unknowns, yung abscissa at saka ano yung weight. All right? So dun sa system na i-develop natin, yun yung mga isosolve natin. Okay? And then if you have n points, implying you have 2n unknowns, this will get to it will get you at most a 2n minus 1 degree of precision. Okay? So it can be shown, though we will not prove it in class, na kapag ka meron kang endpoints na ginamit, yung maximum degree of precision ay 2n minus 1. Okay? So in deriving the wi's and the xaby's, we must guarantee that this quadrature formula or this equation involving the integral and the quadrature formula should be true for all polynomials of degree 2n minus 1 or less. But again, we have remarked a nice way on how to do that. We just need to guarantee that the formula will give exact value for the integral of 1, x squared, until x to the power 2n minus 1. And if we'll write down these equations, okay, so we will get a system of 2n nonlinear equations with 2n unknowns. Unfortunately, hindi ako masyadong magdudwell kung paano isolve itong nonlinear system na to. Siguro pag n equals 1 o kaya n equals 2, manageable pa siya isolve by hand using tools that you learned in your algebra classes. Pero if n is large, medyo mahirap na siya kasi halimbawa n equals 5, you're gonna get a 10 by 10 linear system. Each of those equations might be nonlinear, or at least 9 of them would be nonlinear. So medyo tedious siyang gamitin. So for now, we will rely on MATLAB to give us the solution, or you can use any online solver that you find that can solve a system of nonlinear equations. So hanap na lang kayo sa net, or I'll show you a quick code on how to do it in MATLAB, okay? Kasi yung ibang methods for solving nonlinear systems ay nasa Math 175 pa. So don't worry kung malaki yung system na ipapagawa siguro sa Excel or yung makikita nyo sa problem set later. Hindi nyo siya kailangan gawin by hand. Search lang kayo sa net ng isang solver na pwede nyo gamitin, or you can also use MATLAB. Okay? Okay, so I think I've been talking for 25 or so minutes now. Puro theoretical at puro conceptual. So let's do some work here, some actual work. I-derive natin yung Gaussian quadrature formula for n equals 1. Ibig sabihin, isang point lang yung gagamitin ko. So kung isang point lang yung gagamitin ko, itong quadrature rule na ito, okay, will just have one term. That would be W1 times f of x sub 1. Ang question ngayon ay, ano dapat si x1 at ano dapat si w sub 1? So meron akong 1 point na gustong gamitin. That will give us what? That will give us two unknowns, W1 and X sub 1. And this will give us a formula of degree of precision 2 times 1 minus 1. So that's going to be degree of precision 1. So ibig sabihin, kailangan ko lang piliin si W1 at saka si X sub 1 para yung quadrature rule ay kaya niyang i-integrate lahat ng polynomials of degree 1 or less. Okay? So dahil degree 1 or less, dapat eksakto yung ibibigay niya sa aking integral para sa integral ni 1 at saka sa integral ni x. Ito lang yung kailangan kong i-guarantee by the linearity of the integral operator. Okay? Now, let's see how the nonlinear system will look like. Okay? Now, una, gawin nating f of x equals 1. Okay? So dito, i-plug in natin si f of x ay equal kay 1. So kung si f of x ay equal kay 1, so we'll have integral from a to b of dx equals w1 times si f ay constant function 1. Pag pinlogin ko si x1, 1 pa rin yung makukuha ko. Alright? So this equation, particularized for f of x equals 1, will look like this. So w1 times 1 will give us w1. Medyo na-flip yung equation ko rito. Pero itong integral na to, madali siyang evaluate. Integral lang ng dx, that will give us b minus a. So basically, our first equation is w1 equals b minus a. Okay? And then next, again, since the formula promises to be to have degree of precision 1, it should also give us an exact integral for x to the power 1. So to get the next equation in our system, I'll need to plug in x equals 1 into the quadrature formula. Okay. Now this would be integral from a to b of x dx equals w1 times f of x1. But f here is the linear function x. So if I plug in x1 into x, I'm going to get x1. Okay. And so we'll get this equation. Now we get w1, x1 on the first side of our equation. And then if we evaluate the integral of x over the interval ab, we're going to get b squared minus a squared all over 2. Okay. And this would be the linear system that we need to solve to find w1 and x sub 1. Luckily, it's not that hard to solve it by hand kasi given na yung value ni W1, remember B minus A are the B and A are the upper and lower limits of the given integral that we want to approximate. So these are constants given in the problem. So W1 is already solved. It is equal to B minus A. Now I'll use that information in the second system. So I'll get B minus A times X1 equals B, B squared minus A squared over 2. I can divide both sides by b minus a. So the b minus a will go there. B squared minus a squared is just b plus a times b minus a. So this guy simplifies to b plus a over 2. Okay? So that means the CSA that we should use is the midpoint of the integration interval used. So that's going to be a plus b over 2. And the weight associated to it is b minus a, the length of the interval. So plugging this back into our form or our ansatz for the quadrature rule will give us this guy. Okay, ito yung 1-point Gaussian quadrature rule. And incidentally, this is also the midpoint rule. And this rule is guaranteed to give us the exact integral for any polynomial of degree 1 or less. Okay? Okay. So guys, do you have some questions before we proceed further? Clear ba yung derivation? I hope you get the idea, all right? Kasi kung mapapansin nyo, or dapat napansin nyo na by now na sa exercises or sa problem sets, hindi lang talaga kayo nag-a-apply ng formulas. You are trying to derive the formulas. So I am illustrating it for the simplest cases in the module, and I hope you can extrapolate the pattern from there and derive corresponding formulas or corresponding methods on your own, okay? So do you have any questions or is everything clear so far? Okay, thank you, Narisa, for the thumbs up. So now, okay, mukhang maganda naman yung process. Kailangan nyo lang talagang maging patient para i-carry out itong process at saka yung pag-solve ng system. But beyond that, yeah, it seems that we can derive any Gaussian quadrature rule for any number of points. All right. Pero we can further um, simplify the process by normalizing the integration interval AB into the integral -1 to 1. Kasi mapapansin nyo, ang ginagawa lang natin yung right-hand side nung equations natin. Actually, dun sa nonlinear system, yung isang side niya ay laging integral ng mga x to the power n. Alright? Supposedly over the interval AB. Pero we can perform a change of variable so that the bounds of the integral will be from -1 to 1. And if that would be the case, then it would be easy to integrate at least the odd powers of x to the power n. Kasi kapag ka-odd yung function, yung integral niya over the interval -1 to 1 ay equal lamang kay 0, hopefully making the system of nonlinear equations much manageable. Okay? So, ito yung usual trick. So, ang ginagawa natin ay nino-normalize natin yung integration interval. We're choosing the abscissas from the interval -1 to 1. And then, if we are dealt with an integral over an arbitrary integration interval AB, then we're going to use the same technique na ginamit natin para i-translate at i-scale yung roots ng Legendre at saka Chebyshev polynomials. Para yung interval -1 to 1, mas-scale natin pabalik dun sa interval AB. Okay? And that is more obvious in integration because to achieve an integration interval from -1 to 1, okay, what we can do is to perform this easy change of variable. We let x to be b minus a over 2 times the new variable t plus a plus b all over 2, where the value t here is guaranteed to is chosen over the interval -1 to 1. Okay? So para yung interval AB manormalize into the integral -1 to 1. So this will give us dx equal to what? B minus a over 2 dt. And plugging this substitution into our integral of f over the interval AB, ganito lang yung mangyayari. So meron kang function, pinalitan natin yung variable sa loob niya. Instead of x, we use this function of t. So kailangan ma-multiply by the derivative dx over dt. Okay? So ito yung usual substitution formula. So, but we know that dx over, we know that, what? Yeah, we know that dx over dt is b minus a over 2. Ito yung function times dt. Alright? So ito yung gagawin natin. I-derive ko yung abscissas. So yung mga abscissas ko ngayon, sila yung mga t values. So t values would be the abscissas in the interval -1 to 1. Okay? Tapos pag na-compute ko itong mga t's sa interval -1 to 1, para ma-evaluate ko yung integral from a to b, gagamitin ko itong formula na to. So ang gagawin natin, magde-derive tayo ng Gaussian Quadrature Rule para sa interval -1 to 1. Okay? So ibig sabihin, yung mga abscissas na mako-compute natin ay from -1 to 1. Tapos kung yung gusto kong i-integrate na function ay over the interval AB, kailangan ko lang gawin ito. So, scale ko siya ng b minus a over 2, tapos gagamitin ko yung quadrature formula para sa interval -1 to 1, but the inputs to the function f should be translated this way. Okay? Probably we can look at it later. Tingnan muna natin paano natin ma-develop yung Gaussian quadrature rule. So let's go to the next simplest Gaussian quadrature rule. That would be the one using 2 points. Kung gusto natin gumamit ng 2 points, ibig sabihin meron tayong 4 na unknowns. W1, W2, X1, and X2. Okay? And then we expect those 4 unknowns to be involved in 4 nonlinear equations. So meron tayong 4x4 system. And then since we are using 2 points, we expect to get a quadrature formula of degree precision 2 times 2 minus 1, or 3. Meaning it should be able to give us the integral of 1, x, x squared, and x cubed exactly. So mula dun sa statements na yon, makukuha natin yung apat na equation para dun sa system. Okay? Now, since we are using 2 points and we are doing everything over the interval -1 to 1, so our quadrature rule should look like this. Okay? W1 f of x1 plus W2 f of x2. Kasi nga 2 points yung gusto natin gamitin kay Gaussian. Tapos dapat mabigay niya yung integral ni f over the interval -1 to 1 exactly, where f is a polynomial of degree 3 or less. Okay? Pero magte-take advantage na naman tayo nung linearity nung integral operator. Ibig sabihin, dapat pag pinalitan ko si f ng 1, ng x squared, at ng x cubed, dapat totoo itong equation na to. Okay? So first, if we will replace f here by the constant function 1, so we'll have the integral of 1 dx from -1 to 1. That's how we got that in the first equation. And then we will replace the f by 1. W1 times f of x1 is still 1. It's a constant, so you get W1 there. And then here, f of x2 will be replaced by 1 as well. So we'll have W1 plus W2 equals the integral of dx over the interval -1 to 1, and that is equal to 2. Okay, next step, we will replace the f by the the linear polynomial x. So ito magiging W1, tapos si f ay magiging x evaluated at x1 plus W2 times x evaluated at x2, all right, equals the integral of x over the interval -1 to 1. Okay, but the integral of x over the interval -1 to 1 is just equal to 0. And that's why we have chosen the interval -1 to 1. Para yung x to an odd power will have an integral equal to 0. Para medyo mas madaling isolve yung system. Okay? And then we can also do the same thing for x squared. So if we replace f by x squared, if you look at the quadrature rule, it's going to be W1 times the function value under x squared of x1. So that's going to be x1 squared plus W2 times the function value of x2 under the quadratic function x squared. So that's why we have this side in our equation. Okay. And then this guy will just be the integral of x squared over the interval -1 to 1. And performing the integral by hand, you're going to get 2/3. Okay? And the same thing will happen for x cubed. And again, I'll stop at x cubed because the promise of this Gaussian formula is that it will be of order 3 or degree of precision 3. Okay? Now, our problem now is how to solve this system of nonlinear equations. So yun yung challenge. Mahirap na siya gawin by hand. Pero luckily, manageable pa siyang gawin kay MATLAB. Of course, you can use any online solver or any software or app that you have. Some other options are Wolfram Alpha. Punta kayo sa net, meron silang online solver. Or if you have Mathematica installed in your laptops, that's I think that's better than MATLAB kasi mas designed siya sa symbolic calculations. But let me illustrate this process using MATLAB kasi MATLAB yung sure na meron tayong access lahat kasi may free subscription ng UP. So I hope this is clear before I shift screens. So lilipat ako sa MATLAB. So hold on guys. Let me see where my MATLAB tab is. There you go. So I hope you guys can now see my MATLAB screen. Hopefully hindi rin siya ganun kaliit. Okay. So una, kailangan ko i-declare yung mga variables. So kailangan ko i-declare yung mga symbolic variables na gagamitin natin. Typically, these are just the unknowns. So it's going to be x1, x2, w1, and w2 kasi ito yung mga isosolve natin. Okay. And then MATLAB has a nice solver, symbolic solver actually for system of equations. Kaya niyang isolve yung mga simpleng nonlinear systems katulad nung meron tayo rito. So the syntax for that is, of course, kailangan kong i-store yung answer. Dahil meron tayong apat na hinahanap na unknowns, I will store the solution to the system into a vector consisting of 4 entries. Tapos i-order ko na lang siya na x1, x2, w1, and w2. So ibig sabihin, yung sagot dun sa nonlinear system ay i-store niya sa vector na to. So yung x1, x2, w1, w2, ito yung mga values na masasolve niya. Incidentally, naging kamukha na siya nung symbolic variables na in-introduce ko later, but that won't be too much of a problem because the output here is also symbolic in nature. Okay. Tapos yung syntax or yung function na pang-solve ng linear system kay MATLAB, ang pangalan niya lang ay solve. So you type solve, and then solve will have two vector inputs. Okay. So ano yung dalawang inputs niya? Yung unang vector input niya ay yung mga equations dun sa system. So type nyo lang ano yung equations na nandun dun sa nonlinear system natin. So I'm referring now to the notes on another window. Okay? Kakopyahin ko yung system. So yung unang equation sa system ay W1 plus W2. Kaya lang sa MATLAB sa equations, yung equal sign dapat ay double equal sign. Kasi yung single equal sign ay para sa value assignment. And since we are declaring an equation here, so dapat double equals yung gagamitin nyo. So it's going to be equals 2. All right? So yun yung unang equation. Pangalawang equation ay W1 times X1 plus W2 times X2. Right? And this should be equal to 0. Okay? And then third equation is W1 times X1 squared plus W2 times X2 squared. And this guy should be equal to 2/3. Okay? Equals to 2 over 3. And then the last equation is W1 times X1 cubed plus W2 times X2 cubed. All right? And this should be equal to 0. All right. So yung mga system of equations, ilagay nyo siya sa brackets kasi iisipin ni MATLAB na sa isa siyang vector. So vector of equations separated by commas. And then the second input would be the vectors of the variables that we want to solve for, right? Para alam ni MATLAB sino dun sa mga equations ang mga variables. All right? So ang sinusolve natin ay si W1, W2, X1, and X2. Pero make sure i-order niyo siya ng tama. So dahil ang order ng output ay X1, X2, W1, and W2 yung nandun sa left-hand side ng value assignment, kakopyahin ko na lang to para same order yung pag-output ni MATLAB. Okay. So dito sa loob ni solve, alam ni MATLAB na ang sinusolve niya ay si X1, si X2, si W1, at saka si W2. Alright? So ito yung mga sinusolve niyang variable. And then yung unang output dito ay si X1 kasi siya yung nauna dito sa declaration natin dun sa solve function. So si X1 yung unang component. So ibig sabihin, ilalagay niya kung ano man yung masolve niya para kay X1 dito sa unahan ng vector. Okay? Kasi pwedeng halimbawa A yung pinangalan ko dyan. So yung solution, yung isa dun sa mga components ng solution ay magiging A all throughout this MATLAB code. Pero ano yung mapapa-assign kay A? Ang mapapa-assign kay A, dahil si A yung una dun sa left-hand side, siya ay mapapa-assign dun sa unang outputs declared, dun sa unang output ng algorithm declared under X1. Okay? Kaya dapat magmamatch yung order netong nasa loob ni solve at saka nito nasa variable na ginamit. Pero for simplicity, X1 na rin yung gagamitin ko para sa kanya. Okay? And then we can just hit run here. Solve yan ni MATLAB. Okay, there we go. Tingnan natin yung output. Okay. So actually here, MATLAB gives us two values for X1. Okay? So ibig sabihin, may dalawang posibleng solutions pala to. So meron dalawang quadruple solution etong system na to. So yung unang X1 ay si square root of 3 over 3. Ang kapartner niya na X2 ay si negative square root of 3 over 3. Yung associated weight para kay X1 ay 1. Yung associated weight para kay W2 ay 1 din. Okay? Now, yung second quadruple ay negative root 3 over 3 and positive root 3 over 3. And if you notice, this is just x1, the previous x1 and x2 in reversed order. So, kasi symmetric yung equation, yung nonlinear system na nakuha natin. So, posible na pagbaliktarin mo lang din si x1 at saka si x2. But anyway, the weights given there are also both equal to 1. So, no problem there. So, essentially, we have the same solution. Kahit dalawa yung binigay na system, binigay na solution dun sa system, they're actually equivalent to each other kasi nabaligtad lang yung roles ni x1 at saka ni x2. Okay? So if you want to have a prettier output, pwede nyo gawin ay pretty. Pwede nyo idagdag dun sa code. Lagay nyo ay pretty. Kasi lalo na kung mahaba yung expression, baka mahirap siyang kopyahin mula kay MATLAB. So pwedeng pretty. Tapos ano yung gusto mong ipa-display sa kanya in a pretty symbolic fashion. So halimbawa itong vector na to yung gusto kong ipa-output sa kanya. Okay. So dahil na-compute na naman ni MATLAB lahat except for the pretty output, i-run ko na lang to evaluate selection or I can hit F9. Now I'll get this. So this is much clearer insofar as harvesting the quadruple. So makita nyo meron talaga siyang dalawang quadruple solutions. The first solution is a square root of 3 over 3. For x1, for x2, you have negative square root of 3 over 3, and then the associated weights are 1 and 1 respectively. Tas yung pangalawang quadruple ay ito naman. Okay? So that's basically how you solve a nonlinear system symbolically in MATLAB. It works fine for a small system. Ito 4x4. You can try to push its limit. Tingnan nyo kung gaano katagal yung 5x5. Actually, lagi palang even tayo, no? Yung 6x6, 8x8, and 10x10. But of course, since this is a symbolic calculation, which is very much expensive computationally for machines, medyo may limit yung laki ng system na kaya nating ipasolve kay MATLAB using the solve algorithm. Kasi itong solve algorithm ay symbolic. So meron mga numerical techniques on how to solve system of nonlinear equations. Kay MATLAB, pwede nyo itong palitan yata ng fsolve. So yun ay isang numerical technique. Pero kasi yung konsepto ng numerical techniques for solving nonlinear systems sa Math 175 pa natin i-discuss. So kaya symbolic muna yung gagawin ko rito. Medyo inefficient itong symbolic. So, but ang kagandahan sa kanya, eksakto yung solution na makukuha natin. Okay? So if you guys want to take a screenshot of this little code I wrote here, so you can do so before I shift to the PDF for in 30 seconds, okay? So screenshot this portion first, then I'm gonna scroll to the right para makita niyo yung kalahati ng mahabang solve code, okay? So 5, 4, 3, 2, 1. Then I'll extend it here for the rest of the line. Okay, you can screenshot it now. Okay. Okay. Any questions about the MATLAB code? I hope it's clear. 3-liner lang naman yung code. So don't forget the symbolic declaration here para alam ni MATLAB na symbolic variables si x1, x2, w1, and w2. Kasi otherwise, hanapan niya kayo ng constant value. Okay. So let me switch back to our work text here. Okay. Now we got this solution from MATLAB. Pinili ko yung second, yung pangalawang quadruple doon. Ang x1 ko ay negative root of 1/3, which is the same as negative square root of 3 over 3. Okay? And then si x2 ay ito. Tapos si w1 at saka si w2 ay parehas equal kay 1. So that means these are the desired abscisses and these are the weights associated with them. So in summary, the quadrature rule or the 2-point Gaussian quadrature rule that is of degree of precision 3 is given by this guy. Okay, so whenever you want to approximate the integral of a function f from -1 to 1, you can just perform this formula. Okay, so evaluate the function at negative root of 1/3, add it to the function value at the root of 1/3, Ang associated weights lang naman sa kanila ay parehas 1. So kaya wala na kayo nakita ng non-unit constant multiplier there. And yeah, that would be your approximate for the integral of f over the interval -1 to 1. Okay? So let me borrow 4 more minutes para kasabay tayo ng kabilang section. I-illustrate natin kung paano natin siya kayang gamitin. Of course, if the integration interval in your problem is from -1 to 1, and then you're good, mag-evaluate ka lang ng dalawang function, pero ang x sabies na gagamitin may plus or minus root of 1/3, add them up, then you get the approximate. But what if you have an integral over an interval other than -1 to 1? So let's revisit ln2 again. And we said in our Newton codes discussion last time, yung ln2, pwede nating i-compute as the integral of 1 over x dx from 1 to 2. Okay? Tapos, kung gagamitin natin yung two-point Gaussian quadrature, ito yung formula ng Gaussian quadrature. But obviously, this will not fit in right away into our integration interval kasi ang integration interval natin ngayon ay from 1 to 2. Okay? But from the variable substitution that we have performed earlier, alam natin na yung integral from a to b ay equal lamang dito. Okay? So ito yung normalization ng interval AB into the interval -1 to 1. Now, if f of x is equal to, oops, sorry. Yari. Okay. So, ang function natin ay 1 over x. Tapos, ang t-values natin para dito sa formula na to ay yung na-compute natin na abscissas. Alright? So, compute b minus a over 2. Alright? So, siya yung nandun. Tapos function value siya supposedly at the computed abscissas, plus or minus root of 1/3, right? Pero dahil yung original integration interval natin ay AB, so instead of plugging in plus or minus root of 1/3 into the function f, ang ipa-plug in ko kay function f ay yung translation nung t-values, which are your plus or minus root of 1/3, into the interval AB. So gagamitin ko tong formula na to, which is basically, if you recall, this is the same formula as what we used for the Legendre and Chebyshev nodes whenever we want to interpolate a polynomial over an interval other than -1 to 1. So ibig sabihin, I'll have b minus a over 2, that's 1/2, times the first abscissa that we computed for, negative root of 1/3. So that's how I got this, plus a plus b over 2. Plus, yung weight ay 1, times the function value, supposedly at positive root of 1/3. However, the integration interval is not -1 to 1, so I need to translate root of 1/3 to a number between between 1 and 2. So gagamitin ko ulit yung formula na to with t equals root of 1/3, I get this. Tapos, etong value na to, etong ipa-plug in ko kay f. Etong x value na to, ito rin yung ipa-plug in ko kay x. And what we get from this calculation is this guy, up to some degree of precision. Okay, and this is pretty close to the actual value ng ln2. Actually the relative error is just 0.12%. So this produced a very nice approximation for ln2. Okay, so hindi tayo sure, or actually nakita natin dito na hindi eksakto yung binigay na value nung quadrature rule. Kasi nga ang promise niya lang, kaya niyang ibigay eksakto yung integral ng lahat ng polynomials of degree less than 3. Pero yung less than or equal to 3. Pero yung pina-integrate natin sa kanya ay hindi polynomial. Wala pala itong dx. Ay hindi polynomial. Alright, 1 over x. So, but even though that's the case, we still got a good result, all right? 0.12% relative error. Okay? So I think that discusses the bulk of Module 9. Next time will be very short because I'll just be talking about a generic, I'll show you this generic table for the Gaussian weights and abscisses. So isip pa ako siguro kung may madadagdag akong masasabi, pero kakonti na to. And we'll have just one more example. And I guess with that, you should be prepared for Lab Exer 5.2. Okay? So I think that's it for today. Do you guys have some questions? Meron bang hindi malinaw? I hope your silence means gets na gets yung diniscuss natin today. Okay, so if that's the case, then thank you guys for joining me today. Enjoy the rest of the day, and let's see each other again on Friday to finish module 9. Okay, bye guys.
Thank you po.